I'm Audrey Chen, and this is my entry for the 2023 Department of Defense Student Video Showcase Challenge. I'll be covering data structures in AI today. Come with me. We start with the node. A node is a basic unit of data structure that contains a value, like a number, state, or string. It has a reference or pointer to another node, and when you connect those nodes, they form your data structure. With that information, we can go to queues, and queues are a line of nodes where the first in is first out, like a McDonald's drive-thru, and that's called the first in, first out property. There are operations associated with these queues, like onQueue, which adds a node to the end of the line, and dqueue, which removes the first node and returns it. Now on to stacks. So unlike queues, which have the first in and first out property, stacks have the first in, last out property. We can conceptualize it like the backspace button on a keyboard, and the last letter of a word that's typed out will be removed first. For stack operations, we have push, which adds a node to the end of the data structure, and pop, which removes the node. The final structure I'll cover today is trees, and I'll see you in a second. The last structure we'll cover here is a tree. This is a search tree. What's different from queues is the structure may have more than one pointer to another node rather than just one. We read the tree from top to bottom from the first node, the root. These are the parent nodes, and these are the child nodes. Potential outcomes after the state of the parent node. The branching factor is the maximum number of children a node can have. In this tree, the branching factor is 2. The depth is the number of levels of the tree, so the depth of search is 3. Let's see examples of tree searching strategies. Here's our search tree, otherwise known as a state space. A depth first search always expands the deepest node first, and once that last node is visited, it backtracks to its parent node if no sibling of that node exists. In a breadth first search, the highest unexpanded nodes are prioritized, and it expands from top down. As for the application of these data structures in AI, queues can be employed in various scenarios, such as task scheduling, managing job execution, or handling asynchronous processes. For example, in reinforcement learning, queues might be used to store experiences for training a model. The application of queues in AI depends on their specific problem and their need for organized task processing. Stacks facilitate efficient memory management during recursive operations in a common paradigm in AI. The ability of stacks to manage function calls aids in handling complex text by organizing the execution context. Additionally, stacks find utility in parsing expressions, a task inherent in AI applications dealing with mathematical computations or programming in languages. Trees play a fundamental role in AI, particularly in areas such as machine learning, decision trees, and search algorithms. In machine learning, decision trees are employed for classification and regression tasks, providing a structured way to make decisions based on input features. Hierarchical tree structures are used in natural language processing for organizing semantic relationships, such as in the case of syntax trees. Search algorithms like Minimax and GamePlank AI, or decision-making processes in robotics, often utilize tree structures to explore possible outcomes and make optimal choices. Overall, trees in AI offer a systematic and efficient way to represent and analyze complex relationships and decision pathways.